Okay, so we're gonna continue Ferrous Alloys. So this is Unit 4, Part 2. So when we say ferrous alloy, in industrial material, we're concentrating iron and steel. Okay, and non-ferrous alloy in industrial materials, we're talking about everything else in your elements except iron and steel. Okay. So non-ferrous is all other elements in the periodic table. When you take iron and steel out, and that is going to be your ferrous alloy. Mostly iron in periodic table, by the way. We call it steel because iron has some carbon in it. Okay. Alright, cast iron. So when you think about a cast iron, this is what you usually picture in your head, yeah? But that's what we use. So iron, we're gonna put about 2 to 4% carbon, and then we're gonna add like 1 to 3% silicon, and then some other alloying elements in trace. So we use a cast iron because it's really low cost. You call that cast iron because it's easy to cast into complex shapes, right? There like there's a one student asking me about this, and I remember. So what we do is first we take the elements out of the ore and then refine them, right? And then we do some treatment on it, and then we're gonna make either raw shaped sheets, okay? And then we ship them out to the manufacturers. They're gonna use this, and they're gonna fabricate it, okay, into different products. So that's basically, I want you to picture that big picture in your head, okay, where the materials come from. And they're very expensive, even for getting this one sheet, okay? So if an artist is gonna buy a sheet, then he or she can do a lot of this, okay? If the construction people buy this, then you're gonna get all that city buildings, yeah? The regular residential, they mostly go with plaster and wood, yeah? You might have like a good foundation and then the frame, but most of them are, I think, definitely wood material, yeah? Okay, types, cast iron types. White cast iron, we have gray, and we have malleable cast iron, and we have ductile, and we have high alloy. Okay, 5 of them. So if I ask you in the test, then you should get this, yeah? Test is gonna be a little bit hard for you to take it because even if they're like open book, you still have to know where the materials are. So if you don't read it, you're gonna have an issue, yeah? So make sure you read your lectures so you know where the materials are on what page, okay? Try to practice that. It's not really easy to take an online test, yeah? You can also come to my class and take the test on paper, so that's up to you, yeah? Okay, white cast iron looks like that. So white cast iron is nothing but, again, we're looking at these concentration, how much we're putting in to the iron. Yeah, so we're gonna put low percent of carbon, low percent silicon, and some trace alloy elements. The procedure. So carbon is gonna form iron carbide as usual because iron and carbon, they're gonna react to each other and form a compound. Iron carbide, we call it cementite, came from previous lecture. Then they're gonna solidify, becoming solid, right? And they have really high solidification rate, meaning like they become solid real fast. And don't forget we're heating, okay, and making it molten, and then they become solid at a fast rate. Why? Because this carbon is really low, okay, and this also silicon is very low to go into iron. Quality. They are wear resistant, they are hard, and they're breakable, meaning brittle. Yeah. So uses here, where do we use a white cast iron? We use them in grinding balls, mineral mill, the farm equipment. Okay, if you go to the farm, you're gonna see all kinds of farm equipment giants, yeah, and roller dies. So again, don't forget the percentage. Don't forget how they change in properties or quality, we call them, and then where we're using. Okay. Gray cast iron now still in low percent. Okay, low percent. So what's the difference? So here we're going to stop in the process. So the carbon is going to separate to graphite flakes. So when they turn from molten to solid, okay, they're going to separate into graphite flakes and then form some grayish, okay, grayish cast iron. And we call that because of that little gray surface, we call that gray cast iron. So in the previous slide, the white cast iron, we stopped at the really high solidification rate in the process, and they turn, like the surface turn white. Okay, that's why we call the white cast iron. Here is gray because of the graphite flakes. Okay, and that happens sometimes in solidification. I believe that's because of this carbon and silicon percentage. When we play with it, okay, if the graphite flakes come out and mess around, then we're going to call gray surface, and you see the gray surface, we'll call that gray cast iron. Okay, you play around with the low percent carbon and silicon, and you got a white surface, we're going to call that white iron. Okay, a little more pure. We use them in a complex machine basis. Yeah, giant machine basis. So the construction, there are two major, right, types of construction. One is for the residential and the other one is commercial. And in commercial, we have two different types again. So commercial buildings and commercial systems. Okay, systems are when we build the factories, okay, bridges and things like that. So at that time we use a heavy, okay, complex machine basis. So when you build a system, what happens is like your system is either processing something, usually it's a manufacturing factory, refinery place, or the gas. Okay, gas mean your gasoline I'm talking about. So if you go to the Exxon plant, you're gonna see we also have a electric power grid. Okay, and they all come with those kind of basic you need. Nuclear factory, the same thing. Okay, and they need real high corrosive resistance and high oxidation resistance, and we need a pretty good quality metal to do that. Okay, so that's where these guys come in. For our houses, like residential place, we don't need that much of stuff. Okay, they use the cheap stuff. Ductile cast iron is a nodular cast iron, so still the same, low, okay, percent carbon, low percent silicon. And here we're gonna spike magnesium, very small percentage, and other rare earth metals. Okay, that depends on the descriptions. We now learn only general, okay, elements, but when you actually produce, then you have a different, okay, combinations to make a different quality cast iron. So the carbon again, in the iron was molten, and the iron is going to solidify in the solidification, okay, process. And sometimes carbon form nodular graphite. Okay, there's a little nodular, like little round thing you can see in the graphite, and then that will give quality, okay, ductile quality in cast iron. Yeah. So what happened during solidification matters, and it differentiates into three categories of cast iron. White, nothing happened. Okay, gray, graphite flakes. and ductile cast iron, we call it nodular. You got the nodular graphite, okay, and during the solidification stage of the process. We're going to take a look at the quality, which is your property, high tensile strength, so therefore it is tough. Uses, we use like a crankshaft, okay? You can see this in your engine, car engine. The cars are pretty durable. You can drive like 20 years if you maintain them. If you don't maintain, you can drive about like 10 years, yeah? So why? Because we use good quality industrial materials, yeah? Okay, what's the advantage? They have like a very low production cost, and they also, you can cost them easily. So good costability, okay? So we learn graphite flakes in solidification process, and we learn nodular graphite, okay, in solidification process that differentiate between gray cast iron and ductile cast iron. So here we have some diagram for you. So this is your graphite, okay, flakes morphology, and then that is your nodular graphite morphology. Okay, see how these nodules are right in there. Here is a little bit flaky, okay? Okay, high alloy cast iron, still the same. Okay, low percent silicon carbon, but we're gonna bump the alloying element. Okay, so why are we bumping in the high percentage of alloying elements is because we want to have quality, okay? So in order for us to have quality material like high abrasive, high resistance, high wear and corrosion resistance, okay, we're gonna bump this alloying element. We're gonna keep the same, okay, here, the composition to make our cast iron. So if you want like here example, wear and corrosion resistant, then you're gonna bump like 30% chromium or really high silicon content along with iron, low percent carbon, and low percent silicon. So the final product, you want to get high alloy cast iron, okay? So the types are high alloy white cast iron, modified gray cast iron, and ductile cast iron. So where are we using? We use them in mining application. We use them in agriculture. This is a pump, okay? So we use them in chemical pumps. We use them in acid container. So they have to be really, really high abrasive resistant, wear and corrosion resistant, because chemicals, they're reactive, okay? So we want these materials to be really tough. Acid, the same thing, very reactive. So acid container, we don't want to burn them up, and they have to be very, very resistant, okay, to heat, resistant to abrasion, resistant to wear and corrosion, okay? Now let's get into, we always use heat, okay? Heat means fire, because we gotta make metal into molten state. So in order to change the solid metal, okay, into liquid metal, we have to use fire, which is your heat. So there are different types of heat treatment that we do, okay, in order to shape these metal into industrial parts. So all of these types are showing you how a metal is heated and also cooled, okay? So why are they different? Because we have different heating and different cooling methods. Because we want different structure again, okay? Why do we have to change a different structure? Because we expect different material properties, So heat treatment, we have quenching, tempering, Austempering, we have normalizing, and we have annealing and surface hardening. Okay. Okay, quenching is a type of heat treatment. So what we're doing here, we're gonna heat the steel. Steel is nothing but iron with 1% carbon. Okay. Heat it all the way to the critical temperature and heat over it. Okay. And then we're gonna hold it there. Hold it meaning hold at that temperature for a time. Okay. And then we're gonna cool it rapidly, cool it down real fast. So what do we get by doing that? Heat it, bang, okay, beyond critical temperature, hold it, and then cool it down real fast. You got fresh martensite. Okay, that's just a structure, microstructure. And this type of heating process, okay, we call it austenitizing. Okay, I'm still struggling with this throat thing from this flu. Oh my gosh, something is literally choking my throat. Okay, yeah, increases the strain and the hardness. So hardness is looking at the material solidity, how solid, okay, it is. But then when you look at other properties, we see the durability or toughness decreases, and also ductility decreases. And this process also creates internal stress, right? Internal stress are like the material have tendency to crack or to distort, okay? So even though we use quenching in different medium, like quench in water, quench in green, quench the metal in mineral, quench in polymer, or quench in air, okay? So this austenitizing process of quenching is only good for, okay, bumping the tensile strength and hardness. You gotta be careful because we lose the draw, which is your ductility or elasticity, okay? We lose the toughness or durability, and then they tend to crack, okay? Alright. Okay, so tempering is like when we do quenching, right, in heat treatment. So the quench part that we got out of that process, we're gonna reheat. Okay, tempering processes after quench, you got the quench part, and you're gonna reheat it to 400 to 1100 degree Fahrenheit. Okay, so this temperature actually is much lower than the quenching process temperature. And then we're gonna hold it again, yeah, about 1 hour per inch. So it depends on the material size. So every inch you're gonna hold 1 hour, and then we're gonna cool it. Okay, cool it down. And we usually do tempering right after quenching. So why is to prevent that cracking, okay, which is your internal stress. So by quenching method, we get this internal stress, so we have to remove this. But this is definitely not desirable in the industrial material, because it's definitely going to give you issue. So in order to get rid of that internal cracking, you know, we do tempering right after quenching process to make the material less stress inside, okay? Microstructure formed after tempering process, we call that tempered martensite, okay? So when you take a look at the steel coming out of tempering, you can draw better, meaning like they're more ductile. This is not thin, this is wrong than it was before tempering, okay? After quenching. So I'm going to go ahead and fix it so you can see it. So the property again, more elastic, more ductile than it was before tempering. Okay. Okay. Sometimes I lose this pointer. Austempering is another heat treatment. We're gonna combine quenching and tempering. Why do we do it? Is to get the desired hardness and ductility, okay, in our material. So the process, first you quench to a temperature. We're gonna hold that part at that temperature until the transformation is done, and then we're gonna air cool the part. Okay. So the microstructure, the end product, is called the bainite. It's mechanically, it's a tempered, okay, martensite. It will be a little bit difficult for you to remember what martensite is, okay, so make sure you get yourself familiar with these terms in this course. But you get it, okay, because we have like about 3 months, yeah? So the process reduces the quenching distortion. Yeah? Why do we do this combination? Again, we want to get rid of the distortion. But remember, quenching gives a cracking and distortion. Tempering is going to get rid of cracking. Austempering is going to get rid of distortion and cracking. But then it always comes with another thing, which is it's going to create a real taut, strong steel. Okay. Steel is good when it is more ductile. Okay. We want it a band on high temperature. So tough, strong steel is a-okay, but then sometimes they can become brittle. Okay. You will know these things when you go into the industry. Okay. To work. So it depends on what your company is doing. Over time, you will get used to it. Normalizing, so another heat treatment. So first we're going to heat the steel all the way to austenitic structure, and then we're going to air cool the part. So this process is going to produce small grains and finer perlite. Okay, we call that perlite. So if you Google, you're going to see all the time these terms, right? So this perlite has like alternate layers of territe and cementite. Okay. So perlite is softer than martensite and then bainite. So when you take a look at the normalized steel, it's not really very hard and strong as quenched and tempered or austempered steel. Okay, they're kind of a little bit softer. Okay. Alright, the next heat treatment is annealing. So first, you're gonna heat the steel, or you're gonna heat the cast iron to very high temperature, elevated temperature, and then you're gonna cool it slow. Okay, slow enough to prevent hardness. So how do you do that? You turn the furnace off, and then you're gonna let it cool to ambient temperature, and you gotta do it behind closed door. Okay. The process need attention, and those who do this process got to wear some sort of a protective, okay, clothing. So this process produces materials. See, like how she's wearing gloves and everything. Alright, so heat gloves. So produce materials softer than quench steel. Okay. So because quench steel give you like really strong stuff, but then some of the industrial material parts, okay, we want them a little bit softer. So we gotta soften it up by doing annealing. Yeah. Hardenability. We're looking at how easy it is to achieve the martensite structure in the steel. So materials with more hardenability, okay, they can be cooled more slowly. So what are we looking for? We're looking for the strength, the same strength and hardness. Then we're going to add alloy elements. Why do we do again adding the alloy elements? Because we want to improve this hardenability. Okay. Here is a nice diagram, but you don't have to go into detail. So this is just a graph. No need to study anything or remember. Okay, just try to take a look at the material. Look at that. Okay, so these are your elements, and they're your alloy elements. Okay, now you already know manganese, nickel, silicon, molybdenum, chromium, manganese again. So they're just showing this relative effectiveness. Okay, so here you can see relative effectiveness. So what we're trying to do is we're trying to improve the hardenability of steel. Okay, and we use a different alloy elements. Surface hardening. We're gonna harden the surface because a lot of the product you only need the surface, you don't need the inside. So use some techniques to do that. So we usually do surface hardening because sometimes that we want the high wear resistance, okay, without losing the internal ductility. So we want to keep the internal quality, okay, here in this case the ductility, but then we want the surface, okay, to be pretty high wear resistance, okay. So in the process, we're going to heat the surface very quickly and then produce a hard surface layer. We're going to keep the internal structure totally drawable, yeah, with just ductile. So what are we going to use? Manufacturing of nails, gears, dies, rods, belt stems, and valve seats, push rods, your cams and levers, your crankshaft, your camshaft, your axle shaft, and the bearing. Surface hardening technique, there are 5 of them. You have to know all of them. Okay, flame. We use electric induction, laser. We use carburizing and nitriding. That's just using nitrogen. So let's take a look at each one of them. Okay, surface hardening. We're going to start with flame and then induction and then laser. So flame hardening, what you do is you're going to rapidly heat the surface of the steel, okay, with a direct flame until you got austenite, okay, and then you're going to quickly quench it to form hard martensite surface, okay. Make sure you get these 2 terms, right? Go back all the way to the previous part 1 to get it into your head, otherwise you will quickly forget, okay, what they are. You have to do repeated learning to retain the knowledge. Okay, knowledge is something that you can't keep in your head if you do not repeat. Okay, because our brain is again with protein, so you've got to read it or write it or draw something in order for that information to be retained in the brain. Surface hardening, the next one, induction. Same way as flame, but the heat source, since it is induction, is going to come from your electromagnetic field. Okay, again, electromagnetic field, if you picture in your head, it's going to be generated by very high intensity. Your current is again a flow of your electron. So this field induces a current flow in the steel surface. So the surface gains the austenitizing temperature from the heat produced by this induced current on the surface, okay? Then quench that steel to produce a hard surface. So induction heating is the more uniform than the flame heating because flame is a direct, yeah, fire. Induction is you have this current on the surface, so we can more control, right, and give it a uniform, right, induction on the material. We can control better than the fire, than the flame. So to achieve that, induction heating requires like design. Okay, so here look at that design to fit the part. Here is a circular thing, so we design heating coil circular to fit into that part. The same thing here, giant, okay, part right there, the same thing, the induction coil can fit into it, yeah, because we want a uniform heating for that. Laser. So laser is even more controllable because it's kind of like a pointing, so it gives like a real intense localized heat. Doctors, they use it on your eyes to fix your lamps, if you can't see. So this heat, so in industry we use it too, yeah, on surface. So this heat is used to harden the surface. So laser beam speed is usually controlled to travel across the surface. So the localized, look at that, laser sink, okay, heat into the material. So we don't need to do quenching or cool the part. Why? Because if you point this laser to the part, okay, it's completely localized, and as soon as you remove the heat, that heat on the surface disappears into the material. Okay, so therefore we don't need quenching, we don't need to cool the part. So that's one big advantage. And that hardened layer is thinner than that produced by flame or induction. Okay, flame is direct, induction is a little more uniform. There is not localized. This guy is localized, okay? And the heat can dissipate right straight into the material and gone, yeah? So therefore the layer is thinner. Carburizing. We're going to add the carbon into the surface layer by diffusion. And we're going to bump the high temperature all the way to 1550 to 1750. So steel typical carbon content is like 0.1 to 0.2%. Okay, that's the composition for austenitic, okay, steel. So carburizing is going to increase that carbon content, okay, from this range to 0.8 to 1% on the surface. That's pretty high, yeah. Then we're going to quench it to produce a martensitic hard surface layer. So the carbon content in the steel is the same, a low typical, but the surface, they now have a higher carbon content, okay? So hardening only the surface of the steel. And remember, if you have higher carbon content, okay, it's harder, yeah? That's the reason why we're bumping the carbon content, okay, in a carburizing process. So the movement, how do we do that? How do we do that? So the movement of carbon to the surface of the steel in diffusion, okay, we're gonna get it in 3 ways. One is a pack carburizing, second is a liquid and salt carburizing, and the last one is gas, alright, carburizing. So pack carburizing method, so we're all trying to increase, alright, the carbon content, so you gotta move the carbon anyway into the to the surface, because we're hardening the surface, okay, don't forget that. So the part is put into the steel container, and then we're going to pack with granules of activated charcoal. This is our carbon source, okay? And we're going to do the diffusion process. Okay. So the carbon from charcoal is going to diffuse into our material, and that's increase the content of the carbon in that material. And we call this the slowest carburizing pack carburizing. So if I ask you, okay, there are 3 types of carburizing, which one is the slowest? You gotta choose pack carburizing. liquid or salt carburizing is a melted salt. Okay, we will use a melted salt for what? To carry the carbon. Okay, we're going to carry that carbon to the surface because we are hardening the surface, so we want that carbon right up in the surface layer. Yeah, because the more carbon you've got, the harder the material is, which is your steel. Now we're going to use gas to carry carbon. So carbon is introduced through the gaseous chemical reaction. So gas, as you know, is really fast reacting here, and we call that fastest carburizing. So what are we doing? We're going to move the carbon to the surface, and that surface is to be hardened. Right? 3, yeah? 3 types in carburizing. Okay, the last one, surface hardening, we use gas nitriding. Nitriding is nothing but this process to diffuse nitrogen. We're going to diffuse it all the way to the surface because we want to harden this surface. So this diffusion is going to form a very hard iron and nitrogen compound because nitrogen is reactive. We're going to make it react to iron, okay? And then form nitrate. So the process uses low temperature. And we don't have to do quenching. Nitrogen, okay, atmosphere is really good because you don't get oxidation or scaling, yeah? Like in the air, we have a lot of nitrogen. We use it as a cushion, okay, in the air. Because if you have all oxygen on the earth, it's going to be burning, yeah? We have oxygen and we have a lot of nitrogen. The same thing here, nitrogen atmosphere pretty good because it prevents oxidation and scaling. So this nitrate surface, when you look at the hardness of that surface, it's harder. Okay, harder than the hardest tool or carburized steels. So if you want hardest surface, you want a real good knife or making a real, sensitive hunter's knife and things like that, sophisticated gear, we're going to use a nitriding, okay, to harden only the surface, okay, and keep everything internal material intact. Okay, that's it for part 2. Alright, this week is Unit 4 is really big unit. I'm surprised. I don't know why they combine 2 chapters in 1 week. So anyways, I suggest that you do part 1 on Tuesday, and then part 2 on Thursday, and then part 3 on Saturday, and part 4 on Sunday. Okay. Alright. I won't be doing in person for this because it's too much. We can't squeeze it into 2 hours. Okay, we have other final project to explain. So let's just take it easy. Okay, that's it for part 2.